Wonderful. Good. Well, welcome everyone. My name is Rachel Newberry. I'm the program director at Riot. And we are here at Porticos today with Greg Patterson, who's going to give us a great presentation. Couple housekeeping things. We've got folks online and in the room, so we've got a really full house. Thank you all for joining us this afternoon. If you're here in the facility, restrooms are just across the hall here. As I mentioned, lunch will be here shortly, so we will get you fed. But without further ado, we will jump into our Lunch and Learn today to learn a little bit about Porticos, their work, how they approach their design process and working with clients. And we'll, of course, have time for some Q&A and good conversation as well. So yeah, thank you so much again. And thank you, Greg, for hosting us. And I will hand it off to you.
All right, good job. So, thanks everybody for coming, and those online. I know many of you, and appreciate you coming over, and a lot of you I don't know. So I'm going to make the assumption that this will have some interest. We're still a little bit hungry, so you probably will stay awake for at least the first part of it. But what I wanted to kind of go over today was some of the things that a design firm like Porticos might see during the design side, to give you an understanding of, what are some of the challenges and what are some of the cool processes and techniques that we can use during the development process. So let's see if I can get this thing to work. So what we're going to do is we're going to talk a little bit about the key disciplines needed. Now, I'm talking about developing wireless products, so cell phones, radios, pretty much everything today, right? It's got some wireless component in it. But what are really the key disciplines required to do that? Talk about some design challenges. In some of the cohort stuff earlier today, right, we were talking about testing and trying to come up with requirements and things like that. How do you do some of those? I wanted to kind of share some of those challenges that maybe some are obvious and some are not. Looking a little bit at what are the design tasks. Now, a lot of these are focused on mechanical primarily because I've got a lot of cool props to go with it, but we'll talk through some of the other ones as we go along. So people ask during the cohort, like, what's the development process? So we're going to kind of go through that a little bit, not every single phase in it, but in general, from a product design and device development, how do you do that? Look at some of the engineering tools that we use, and then ending it with some fabrication options. This is usually kind of fun, right? Because there's videos that go with it. Some people have never seen an SLA machine run. Some people have never seen, cast urethane or some of these other processes. So I've got some videos loaded up to kind of show how these are done, and talk a little bit as we go through there on why would you use one process over the next when you're developing prototypes for your device. So what are my goals? Basically, I'd like for everybody to at least have an understanding of the importance of close collaboration between the different disciplines. Like, everybody's discipline is the most important to them. Software, mechanics, hardware, most important. But in reality, they have to work together. And if they don't, at the end of the day, one of them might be stellar, but the product itself would not be a real product. Allow you to become familiar with some of the tools that we use and how we use them. And then third, to kind of get a feeling for what are some of the challenges. So I'll stop here and give a little bit of background on Porticos. So Porticos, for those of you who do not know us, we call ourselves a product design and engineering services company. We started in 2003, myself, Sean and Kevin. Before that, we were at Sony Ericsson with some of the people who are in here. We've worked closely with some of you even from back in those days. When they closed CDMA, we decided to start Porticos. And for us, it was a great opportunity. I think at that time, there was 1,500 people who were displaced by that. We were very fortunate that we had good relationships with those people. They spread throughout, the globe. A lot of them still stayed here, but went to all different places. And quite frankly, that's how we were able to stay alive, right? We had this network, and companies like Dell would never hire a little 3 or 5 man shop to come and do design on their laptops and stuff. But one of the people that we knew from Sony Ericsson ended up being at Dell and being at a high level there, and it made the introduction, and we were able to get in there. So separate from this, especially for those who are startups or are thinking about doing this type of a thing, network is key. Having a good network, always I try and treat everybody, the way I want to be treated, because you never know when you're going to see them again, right? We have bad Greg there and good Greg. So I've known Greg Dunko for years, and we've had the privilege of working together in a bunch of different situations. You just never know where it's going to be. So having a good network is definitely key. All right, so let's move on into let's talk about what we're supposed to be. So what are some of the disciplines? Now, this will be an old familiar picture to some, but if you're looking at the key disciplines for developing a wireless product, right? Obviously, hardware and software, that's kind of the core, right? This device is supposed to do some type of a function, not just strictly a mechanical function, but some type of function. Either it's measuring things, or it's tracking things, or it's making calls, or whatever it is. So there's electronics that are in these devices, and obviously, in our case, when we talk about software, we're talking about firmware required to make the device function. So that's key. Most of these wireless devices, they have antennas, many of them multiple antennas. And there's a variety of different ways that you can make the antennas. But it's a very, antenna performance is greatly affected by things around it and how it's packaged. And so you can't just, especially for most of the newer devices, I mean, this one is an older one, an external antenna, but almost all of the new ones, right, your cell phone or whatever, they're all internal antennas. Where are they? What kind of field do you have to protect around them in order for them to function the way they're supposed to? So these groups have to work together very closely. Power. These are all a lot of them are battery powered devices of some type or another. And a lot of times the battery is a large size component of the device. You need to understand, like, what is the use case for the product, because that's going to define, like, the power budget. How long does this thing have to function, and doing what things during that time? Because you want to make the battery obviously as small as you can get away with, because it's weight and size. So you want to make it as small as you can, but you need the device to perform as long as you want it to. Otherwise, it's a balancing act. And then, of course, there's the mechanical side. Generally, we call it anything you can touch, feel. There's internal guts, structures, and stuff that are used. That's usually the responsibility of the mechanical engineer. But as I said from the start, the way this works is we have to have kumbaya, right? All these groups have to, like, love each other and respect each other, and realize that they each have an impact on each other. It's not any good, for the antenna guy to say, hey, I want this big honking antenna, I don't have a place to put it. And there's not good for a mechanical person to say, well, I really want this thing to be the size of a postage stamp, but nothing can fit in it. So they really, and those are obviously extreme cases, but they have to work together closely. And as you might imagine, the more compact the device is, the more that challenge arises. So my advice to people who are working with devices is, get that engagement early on. Don't develop all the electronics off over here by yourself, and then show up to the party and then say, okay, I'm ready, because it's not going to go together. I can pretty much assure you. And likewise, on the mechanical side, don't go figuring all that stuff out without working together. They need to work together fairly soon in the process. So what are some design challenges that we see when we're developing devices like that? Well, physical use or abuse, I'll say, is a big one, especially for handheld devices, right? So the obvious one, right? Everybody has seen this. You drop your phone, and what happens? You get a cracked display. I mean, as you're designing products, then you have to decide, okay, I want it to be resistant to certain things. So you design products to try and reduce potential of this. You do testing earlier on, and a specific type of testing to see if you can make sure that the design is compliant to that. So that's something that's pretty fairly well known, right? There's other ones that maybe are less well known. Maybe we didn't expect for somebody to shove this thing in their tight jeans back in the, well, when this slide was made back in the tight jean day. You know, it just, I mean, we were talking about it earlier, like somebody mentioned, you know, a software use case, you know, a bug showed up. Well, it was a bug because somebody, you know, was not on the wireless and they were just clicking this button a whole lot on the app and it got into some loop, and, you know, that created a situation that they, you know, you wouldn't really plan on, you wouldn't think about it. So, you know, something like that. So, you know, at the end of the day, then that phone, maybe we need to design it so that it doesn't get bent up like that. Another one that's generally pretty obvious to most people are hot and cold, but not just hot and cold like we're using it. You know, this thing's generally going to be flown from point A to point B at some point. You know, is it a cargo hold? Is it heated? Probably not. Or if it's not, if it has to be, you have to think of those things. That doesn't mean the device functions maybe during some of those low temperatures, but it has to endure them. So here's an example. You know, sometimes if you're not careful, it gets too hot. You know, you can have, you know, bowing, cracking, warping of the plastics. There's some seats up here too if you want. I promise I won't bite. There's some up here. And then just miscellaneous stuff, right? I mean, you just throw things around. People are, like we said earlier, it's amazing what people do. Now there are some that are fairly required. I mean, this is for something like this type of a product. So this radio, I'm going to pass these around. This is to kind of give a feel, some of the differences that you can even feel. So you have something like this, which is more of a consumer type of a product that's meant for people to use. Now it's a satellite phone, so maybe it's not everybody has one, but a lot of just regular people have them. Then you have another product that's next to it. So this is kind of a next step up. This would be something that, you know, firefighters and people like that would use. And you can kind of get a feel, oh, wow, this thing is definitely sturdier, stouter than this and heavier. And then you have something like this, which this was designed for Navy SEALs. So one of the requirements is literally that they had to build a part of this vehicle on top of it. I know it sounds stupid, but that's one of the requirements. So so you can kind of, as you pass these around, and I'll just maybe start here and you just pass them, you can kind of get a feel, man, they feel different. And that's the kind of thing you think about when you're designing a product. Because there's no reason to make something that can hold up a car if you don't need to, because it costs money to make that. So it's important to kind of understand where is this being used. Another one that's a big challenge for devices a lot is what they call ingress protection, IP. And most people don't really understand, they hear it, but they don't understand what it is. So generally the IP, the first numeral is dust or ingress of physical objects. We think of it a lot as dust because a lot of devices are set that way, but it's basically solid protection. And the second one, so IP 56, for example, the second number is water ingress. So, for example, the first one, the dust one, here are the different codes, you know, and I won't spend a lot of time because I'm sure you probably don't necessarily care, but it's kind of cool to see. So it goes from 1 to 6. 1, basically, you know, you want to be able to protect a person from getting their arm in a piece of machinery or something like that, right? I mean, so you're designing a product, and I just want to make sure there's not a hole, you know, bigger than 50 millimeters for this particular product. But as you work your way down, right, they get smaller and smaller. You want to make sure you don't, these are more for electric shock, right? You can't stick a screwdriver in there. You can't stick a wire in there and zap yourself. Then once you get down to the lower ones, now we don't even want dust to go in it. On this one, 5, we can let dust in, but it can't affect the function. So when you take this thing apart after this test, yeah, there might be some dust in it, but it functioned. You wouldn't have known it if you didn't take it apart. It functioned just like it's supposed to. And then the last one, no dust is supposed to go in it. You know, for these products like we're passing around, like your computer here, any device that you have, there's holes in it, right? I mean, there's connectors, there's places where you have a microphone, you have a speaker. No dust is supposed to go in these things. So that drives a certain solution. You know, you have to have certain membranes in front of the mics or the speakers. You have to have certain seals. You may have to have specific connectors that are designed that way. Those connectors may cost more than the other connector. And they may be bigger or have other implications with them. So defining what the IP, what ingress you want is important. On the second one, you know, it's more on the water side. So it can be anything from just falling drops of water, right? I just want to make sure if it's happened to be outside, it was a little drizzle or something, it doesn't get wet. This is, we made a point earlier on in the cohort to talk about the fact that some tests, like these military standards and stuff, and even this IP, here's an ingress protection, it doesn't tell you what your device needs to do. You're the one who's defining, hey, I know the use case for this, and the use case is it's hardly ever going to get water on it, so I only need it to be one. And not only that, but I'm saying I know what up is, right? Because in this one, I say that the thing, this is up, and so I only test it that way. And that's perfectly fine. As we talked about earlier, though, you have to determine your level of risk. Sure, your device can pass this, but if you know in reality this thing is going to be on the sailboat, you know, maybe that's not good enough. And if something happens to it in that application, well, you said it could be used on a sailboat. It starts failing. You know, your company is going to be facing some challenges with that. So you need to know what you want it to do, and then there's generally, you know, a test for you, if you will. And they just get harder and harder as you go along. This one being submerged, but this last one, 8, is basically now, not only are you saying, I want to protect it against submersion, but you, the person making this, sets how deep that is. For some of you, I took the tour, and I was showing you where the fire L3 Harris radio, some of the testing we did. So that one is 6.8, IP 6.8, and they chose, but also, you know, some of the standards lent them this way, that it was going to be 3 meters, and it's going to be 3 meters under certain other conditions. So you're the one who sets this. We've done products that are for divers, right? And then you're going down much deeper. So you kind of understand where the product is being used, and then you're the one who sets that. Ultimately, nobody's going to come out and say, well, you should have picked a 10 or a 12 or a 7. But what they are going to say is, this thing was designed for, I'm a diver. This thing says I can go down and dive, you know, 90 feet. I did it, and the thing's full of water when I came up. They're not going to be happy with that. Some people will hear the word NEMA. I mean, the phrase NEMA. So this is just a chart to show you that ingress protection in NEMA, these enclosures, they basically we're talking about the same thing, but with different special decoder ring numbers. Another challenge, you know, most products, I mean, it's funny, you know, some of my friends in here who've been through the earlier days of cell phones, you know, we used to have all kinds of organic shapes, right? Now they're pretty much just rectangles, which is very efficient. But the more organic the shape is, right, the more challenging it is to fit all the stuff in it. So here's a barcode scanner that I'm sure you've seen if you've been to Lowe's or Home Depot or anything. Here's a good example. So yeah, it would be a lot more efficient for this board just to be, you know, square, but it doesn't fit in here. So again, it's a very tight relationship between the team members, the disciplines, to say, okay, I need a little bit here, and we'll remove some parts there and make adjustments. So that, believe it or not, that's a pretty big challenge. So organic shapes and size constraints are a big challenge. Talking about size, you know, how efficient can we pack these things? So this was a product we did a while back, but you know, now there are Apple Watches and all kinds of different things. If you just look at this little watch idea here, basically we were about 85% efficiency. It's 15% of air in this thing. because you just can't. It's not like you fill it up with water, right? So all these little chips are square, so they take it. You can't, they only go certain ways, and this thing's got curves, so you're going to have some loss. But working together, you try and get as efficient as you can in your packaging, because the more efficient you are, the more performance you can get in a smaller overall package. In this case, it took some creativity. There was one of the cellular bands required that the antenna was actually in the band itself and attached through. Now, it has its own cellular band for a different frequency, but those types of things, you can imagine how closely integrated the teams have to be to kind of test and figure that out. Here's one, that radio. Now, there could be some product-specific requirements. Now, this one, I think I have a video of this. So that radio, not the one I passed around, but I can show people later on. It was the first radio. We designed this radio and what they call the speaker mic. In December of last year, it was the first device to meet the new NFPA compliance standard. And they have a whole slew of weird tests. But one of the tests that I really enjoy is the fire test. So I'm going to fast forward through this so we don't have to see the whole thing. But so you're saying this phone has plastic, it's got displays, it's got all kind of stuff in it. So this is one of the requirements, that it passes this test. And when I say pass, when it comes out the other side, it still works. The display you can read, you can use it, you make calls. It's a very challenging test to do, obviously. Let's see if we can get him. I love this guy. Oh yeah, let's pull him into his little chute. Now, to get to this point and do this kind of testing, that's pretty intense for a radio. And that's not even the hardest test that we ended up having to solve.
So you assume the human survived the test too, so that they could use the phone?
Yeah, you hope.
Not necessarily.
But at least the phone works.
Somebody else might pick up that radio and expect it to work.
That's true.
Yeah. So that's what I would call a product specific one. So you're developing a device and you know that there are certain extremely challenging problems that need to be solved. You need to know it up front. To do that took months worth of just thermal analysis, simulation, trying to figure out, how you protect those things. And it's what complicates it further is, okay, you can say, well, I don't want the heat to get in. Yeah, that's fine. You can put it in a bag, but the thing generates its own heat, right? Because it's a working radio, and these things generate heat. So you have to be able to get the heat out, otherwise it just fries itself. So there's a lot of engineering, honestly, that goes into making that. Somebody asked me earlier on, or we were talking about contracts. Can you guarantee, what's one of your things on the contract? One of the contracts on this one was, we said, well, we can't guarantee that we can even pass this test. This test nobody had ever actually successfully done it. So now the customer, L3 Harris, they have a lot of money and they're big and they're bullies and they beat us up until we ended up doing it anyway. But they together as a team, seriousness, we were able to solve it. But again, some things can't be solved within the constraints that they have. So what are some design tasks? Let's work our way through the process of design. So again, I mentioned this earlier with the cohort. First thing that we do at Porticos is try and figure out what are the requirements. And most of the time, some customers will have fully blown out specs, but most of the time it's going to be stuff like this. Customer's going to come in and say, I want it to be small. Well, to me, that doesn't mean anything. You mean like an M&M small? You mean like and what is small? So on our side, then we try and work with the customer to try and put some number, something measurable against this. So in our case with the customer, okay, it's going to be X number of millimeters wide, tall, thick. What is small? They might come in and say that they want it to be light. What is how heavy is heavy? How light is light? So what I encourage people to do who are working with a company like us, because we're not the only, we're not special in this regard. know as much as you can about the use case. What is the end use case going to be? How are people going to use it as best as you know? Then work your way from there and say, okay, well, to do that, this is something that they would like. They would like to be able to put this in their pocket, or no, they can carry this in a briefcase. And those things, then you start trickling your way down. And you decide, okay, well, now we can start putting numbers against this. Maybe we're doing some research and we're like, there's a competitor product in the market and it's this, and we want ours to be better than that. So that kind of gives us a target. You don't have to come to Porticos knowing 50, 75, 10. If you do, that's great. But you have to realize that you are going to be working with us to help define those, because we can't design something that's just small without knowing what small is, so to speak. So generally, okay, we've got our requirements, we got that figured out. Now we'll generally go into ideation. So this shows some industrial design sketches. So generally, we're working with the customer and coming up with all kinds of cool ideas. Usually what happens is there'll be storyboards of different types, and then we review it with the customer, and they may decide, well, you know what, I like this shape here, but I really like that button better there. And then it starts morphing, and it works it down to being a little bit more defined. So here we're looking at aesthetics, ergonomics, things like that. Next thing is, developing concepts. So hardware team, mechanical team, the different teams, and the software, in our case, the firmware folks, are laying out architectures and concepts to be able to do these things. On the mechanical side, I taught like the Mr. Potato Head thing, because you can make this thing in put it together in a bunch of different ways. Maybe some of them are good, maybe some of them aren't so good, and so you're playing around with these different concepts to try and come up with different ways of doing this. At the end of this phase, generally we're going to be making prototypes to try and evaluate, in this configuration, what of the requirements is it meeting? And so mechanics and hardware will come together here. There's different terminology for different companies and what they're called, but generally, you're going to have the board spun in a certain form factor and the mechanics to kind of go with it. And these prototypes, we'll talk about prototyping processes in a minute, but they're not the real thing, so to speak. They're not. This in production. This is just the first shot at what it looks like. Then we're going to move into stuff like actual detail design. So we started with the sketch. We did some concepts, and then ultimately, at the end of the day, for most people, they want something they can sell, and so it ends with production of something that can be sold. Generally speaking, we go through these phases, and there might be iterations on getting to that point. But at the end of the day, we come up with something that's actually a design that's manufacturable and ready for manufacture. And then we do like the design for manufacturing. This is just an example of why it's important. When you're designing a product, you really need to understand what are the manufacturing processes that you're going to use, because each process has a different impact to what's needed. So here's a very simple example. This is a box. It's got a lid, green lid, and a brown box, right? Straight walls. But in reality, this is being designed for an injection molded part. And for injection molding, there's a draft. These things to come out of the tool, for the tool to come out of this thing, it has to have some amount of draft. Otherwise, it gets stuck. When these two parts try to come apart, it'll just get stuck in there. Well, when you run that through the other way, then all of a sudden this lid that fit nicely, it doesn't go together at all anymore. So if you were the engineer and you're just designing this and you didn't know or care about how it was going to be made, you might end up with something very simple like that. It looks great on paper. CAD looks great. In reality, it won't work. So then we generally go from that, after we've integrated the design for manufacturing, into supporting the builds. So you're going to hear this also if you work with a firm like us and we go this far. We're going to want to know, what kind of volumes are you talking about? And the reason we care is because it is going to define, again, how some of the parts are produced. In this case, we're taking this example as an injection molded part. you know, if we have one cavity, meaning when this thing opens and closes, one part spits out, you know, the mold cost might be much lower. Part cost might be a little bit higher. Whereas if you get a lot of cavities, you know, the mold cost must go up, but the part costs come down. It's important to know what your volumes you're shooting for. So if your goal really was 100,000, then that might lead you to say, well, we should start with a 2-cavity tool because ultimately that's the most cost effective for what you're doing. We have a lot of customers that don't like to make the decision on this, maybe at all, or at least very late in the process. And this is why it's important. You know, we're trying to advise them on the best way to produce these parts for their own costs and stuff. You know, a lot of these things have stampings in them. So most people don't know what a progressive die is. Some of you probably do, but it's pretty cool to see. So you start with a full sheet and you end up with a part that's formed. Now, I think I've got it started in a different place, so I think I can switch over to here. Yeah, I got it. And so we want to make this part here. So it's really kind of cool. So if you've never been to a factory that makes these, you know, this piece of machinery is going up and down, bam, bam. And each time it goes up and down, this thing is being indexed one spot. And this tool has little features that then create one little thing in it. Might be a hole, might be a bend, might be whatever's happening. So it starts off as a flat sheet of metal, comes out being this final part. These, again, volume is important. You don't need this kind of equipment and process if you're only going to make, you know, several hundred or low thousands. You might do it a different way. But if you're making big volumes, then you're going to do something like this. And the way you design the part then is driven by the way it's going to be made. Die casting. This one is another way of making like aluminum or magnesium parts. I don't actually have one here, but heat sinks and stuff like that. It's another, again, knowing how it's manufactured drives how you design it. So for die casting, unlike an injection molded part where when it comes out of the mold, it pretty much looks like the real part. On a die cast part, you can kind of see these areas here. So maybe you can see it on the screen. These areas right here. So molten, in this case, aluminum goes in to those areas. And then when it comes out, you see all this extra, they call it flash, but all these runners and extra molten stuff is hanging out of there. So it doesn't look like the final thing. And you might notice in here, like there's no holes in these screw bosses. So die casting then requires some secondary operations to clean it up and make it look like it's finally going to look. Again, you need to understand how you're going to manufacture the part to understand how you want to design it. So if we move on, so looking at now design validation. Again, another question from earlier today. When do you do tests? How do you do tests? So in the first screen, one of the first screens, right, we showed the foam dropping and breaking, right? So obviously drop tests are pretty much every single product that I can remember us designing. We do some form of drop test. For smaller devices, it's based on height. For bigger devices like laptops, it's based more on G's. So you might drop it from a lower level. So it depends on what product you're doing. But you run it through these tests and you try and decide what happened. Did it come out of it and it still works? And what is pass or fail? Is a pass that it comes out of it and it looks just like you started, not a scratch on it? That's going to be really hard. Or, hey, it can come out. We just don't want anybody to get impacted with pieces, shrapnel falling off this thing. Or it could be anywhere in between those. Again, this is something that the customer helps to define. Vibration test. So here's an example of a vibration test. So there's, you know, basically a huge piece of machinery, and we mount this thing in and we just shake it. And there's a profile. And again, the profile is driven a lot by the use case. So if it's going to be in the cab of a truck, it's going to be a different profile. Here's a profile that it would run than it would be if it's in the engine compartment. So trying to harp on the story of what's the end use, why it's so important to understand that, because, you know, it's driving a lot of these. And to solve them requires more time, and in our case, for you, more money. Here's an example of a water ingress test, because I think people think some of them are very sophisticated tests. You know, this one is not particularly sophisticated. I think you could probably do it at home. So this is done. This isn't even done here. This is done. This is a certified test. This is how you officially would do this particular test. If any of you use the first bathroom, it's got a shower in it. On the wall, we have a little thing. We'll hang devices on it and just run it in the shower for a couple of days to see what happens to it. Then we'll go outside and we'll shoot water at ourselves and say, well, how did it do? Before we would take it, to this official test, because, we don't want to waste anybody's money or time. All right, looking at some of the tools, I think we're okay for time, right?
Yeah.
Okay, so obviously for mechanical guys, the big one is CAD, and I was going to share some names here. So SolidWorks, probably everybody's familiar with that name if you understand, have been involved at all. Its claim to fame was it was basically the first CAD software to run on a Windows platform. It's used quite a bit. We use it primarily here. There are some customers that we use Creo with because that's what they wanted, like L3 Harris has Creo. What you'll find, you'll see the years too, right? 95, 88, and then the last one here that I'm showing, there's other ones obviously, but Unigraphics. You can see over time they kind of progress. So Unigraphics is used a lot by like a lot of the big automotive firms, right? It was developed initially, excellent surfacing and strong machining interface, meaning you could take the CAD, go to the machining center, and it would start chewing out one of these parts. So if you have a big company like that has invested a lot of money in the software, well, they don't want me to do it in this software and they don't want to buy that software because they already got this software. So for us, we have to be a little bit flexible, firms like ourselves, to be able to work in some of these major CAD packages. Another tool that we use a lot is finite element analysis, but it's basically simulation. So the radio that we talked about that ran through the fire, right? We did extensive thermal simulation. So we basically are predicting what's going to happen when it encounters a certain amount of heat or different things. And then we will make design changes to try and make that performance better. Now, usually what you'll see is you'll do these kind of analyses and then you'll build one and you'll test it and you'll compare them. Because, right, there's a lot of inputs, a lot of, I don't want to say guesses, but a lot of assumptions that go along the way, right? I'm assuming that I know what this is going to do. I'm assuming this input is right. So you try and do the real thing, compare them, and then you adjust your simulation accordingly so that you basically make your assumptions better. And then you take that assumption model, and now you can take it and make further improvements with more confidence that the next prototype you have will function even closer to the simulation than maybe the first one did. All right, let's move into fabrication options, which is kind of fun. So the first one that I'll go over, 3D printing. And I've got some parts here that I'm going to pass around that talk about all these. So 3D printing, so we have a printer in here, and this is actually Stratus's machine that we have, but we have some other ones. I mean, it's just taken off, right? The technology's just gone crazy. Like you can buy your own kits and build your own 3D printers now. It's really, pretty cool. The neat thing is, you can make parts out of it, and they can, and especially now the materials have come a long way. But as I pass these around, kind of hard to read on the back, but we're going to go through a few of these. This is a 3D printed part versus a molded part, injection molded, versus a cast urethane. So you can kind of get a feel for like the differences in the way they feel. And you know what? I'm going to do the same thing over here. So these are written on there, molded, SLA, and this is a 3D printed part. So, when do you use this? You use it because you can get parts pretty quickly. We can print them here overnight. They make parts that structurally are not, can handle some of the performance. They're not as good as you can see in those parts with some of the fine level detail. I mean, you can make them better than the example I have here, but still they're not as smooth because it's building in layers, and I'll show an example here in a minute. This is a point where I want to talk about what are the prototypes for. A 3D printed part or an SLA, they're not going to they're not going to be able to handle the heat like a molded part does. So we did a product, one of the drug dispensers out there, and they wanted to do some preliminary, we didn't know this, they wanted to submit it for some preliminary FDA type of stuff. And it was subjected to heat, and the thing just worked like crazy. Well, it worked because it's not in the material that's meant to handle that. So that's an example where by understanding what is a prototype for, if it's meant for that, then we're not going to 3D print it. We're going to make it a different way to be able to support that test.
So even if it's the same material?
Even if it's the same. So they're not 100% exactly the same. And the process by which they're made is slightly different. So for example, this is a sped up, obviously, of a 3D printer working. So it's got looks like wire filament, but it's plastic material. It's heated by a heat and it liquefies it, and this thing is going on. Bzzz. That's why you see all these funny little lines in it when you rub over it. So it's building it layer by layer, and then the platen just drops, and it builds it up like that. So that process then is limited to certain level of quality and certain level of precision. And to your question, the materials have gotten much better over the years, but still it's still not to the point where if you really make a real molded part. That said, we're doing a product right now for a woman from Nashville. It's for the equine industry, and there's brackets on this particular product that are plastic. The 3D parts are strong enough to support that. So to save them money, instead of going right to molded parts, we're just printing them. And so their first X number of units will be 3D printed parts. But they aren't subject to high heats or anything, and their use case allows it. SLA, so some of those parts that are pointing around are stereolithography parts. These you can get much better resolution. You can probably see it when you feel, especially on that one there, it's called high res. They're smooth, they're really nice. But even, again, the materials aren't like the real part. In fact, their materials are even more brittle, if you will, than the 3D printed parts. If you've ever seen one of these work, let's see if I can stop this. Where is it? Right here. So in this one, they are making, I'm not going to play the whole thing, it's pretty long, but they wanted to they're basically making this, a mini version of that. So I don't remember which Terminator it was, but you ever seen the Terminator where he comes out of the liquid bath, like, and he's like, Terminator? That's basically what this looks like. So this light that you see is a laser. There's liquid in here. There's a laser, and it's going along, and everywhere it goes, it basically solidifies this liquid. And as it does it, it just keeps this platen keeps dropping down. So it starts the first layer, keeps dropping down into this liquid. And so when you look in it, it just looks like liquid, right? I mean, it's really hard, unless you really pay attention, it's hard to tell that something's even there. But then, once it's, let's see, get almost to the end here. Once it's done doing this thing, it's just like Terminator, man. This thing just comes easing out of this gore. There's your city. Wow. Which is kind of cool, right? So that's another process that makes it nice for being able to make prototypes quickly. We use those primarily for things like sometimes for fit, and just roughly, fit, how do things go together, feel, stuff like that. That's when we use those. Laser sintering is very similar to what we just saw with liquid, but it's actually a metal. So this video is not as exciting. So in the sake of time, I'm not going to show this less exciting video, but it's the same thing as a liquid, but it's just powder. So it's literally a powder of stainless steel with a binder in it. And this laser comes in, and it drops down. And when it comes out, poof, but instead of the cool liquid, it's just dust pops off of it. And then the thing about this type of process is the part might come out that big because it's got this binder in it. And then they take it and they put it in an oven, and they basically, the binder leaches out of it, and this thing shrinks to its final net form, which might be like that. So there are, some downsides to it, right? I mean, generally there's porosity in these parts. So if you're trying to do a sealed vessel, it might not be a great idea. And it's not, it's a little bit better than the 3D printed parts, but surface finish can be a challenge. But there are a lot of medical robotic devices that parts are made this way. And then CNC machine. So this is like a go-to for making parts that are in the real material. So you can get a block of this real plastic, PCABS, whatever you want. You put it in there and you machine it out with this. And these machines are pretty incredible in their ability to let's see where he go to. Here it is. So, I mean, it's just blowing through steel, or in this case, plastic, or whatever. This one, I think, actually is a metal part. So these machines are just going in and they're cutting. The downside to them, these are used a lot for making molds sometimes, or making metal parts or plastic parts. So some of these parts here, actually, I didn't bring the machine one, but again, the advantage here is it can be the real material. The downside is undercuts and small features can be a challenge, especially undercuts, right? If you have if you had something and you were trying to make this in it and it was only oriented this way, right? It's hard to cut in there. So then you have to do more moving of the part in order to get it where you can do some of these undercuts. And some undercuts you just can't make at all. But these machines, and then you'll see the head change in a minute. So it puts a different tool on it. And now it's going in. These are all designed, the unigraphics I talked about before, basically it would come straight out of the engineer's CAD into this. They'd make machining code on it, and then they would put it in and machine these parts. And the last one is cast urethane. Some of those parts showed that. This is also what I would consider not a very scientific version of being able to do this process. We were doing some here actually. August, we used to do a lot of them here of our own. So basically you would take an SLA or something and you literally put it down into a silicon bath. They're going to show it in a minute. So you make a box out of plywood. You take this through SLA that you made and you set it in this box. And then you just fill it full of urethane. Let's see if I can get to where we're doing that. Yeah, so here's the SLA. They're cleaning it up because the master, they call it, you want it to be exactly as close as you can get it to what you really want it to be. You put it in this plywood box here, and you just shoot this urethane inside of it, and it's basically just trapped inside this silicone. And you go and you cut the silicone open, as they're going to show, and you pop it out. Now you've got basically, when you put them back together, right now you've got an empty spot where that used to be. And then you basically go in and you mix up whatever you want to pour in it and you inject it inside of it. And that then creates the real part. So these processes, cast urethane, as I mentioned here, you can make more parts fairly efficiently if you want to. They have pretty nice finish, as you'll see on that part you're passing around. It takes a little bit longer to make them. But there's a place for when you want to use something like this.
Greg, did you guys make that cast urethane part right there?
That particular one, we did not make that mold. We had it done. But we did design this part.
Yeah, it's really hard to build.
It's really nice, isn't it? Okay, last one then is molding. So since I'm focusing on prototypes, I'm talking about rapid tooling. So in the slide I showed earlier, about when you want to know about volumes. This is not meant for volume. This is meant for, hey, I want to make a few thousand parts. A lot of times the customer will use this if they're not sure their volumes and they want to try and save investment, tooling investment. So we might make a rapid tool so they can get a few thousand parts off of it, up to 20,000 or so parts, I guess. And that kind of gets them going. Another time that you might use these is for the case I talked about where we're going to, this prototype has to actually endure a certain test that the other prototype processes can't pass. You might have to spend the money and do a rapid tool so we can get it fairly quickly and somewhat lower cost and get really molded parts. So, yep, here at the end. So, in summary of this thing, basically, hopefully, I was able to convince or show is that, close collaboration is required between all the different disciplines. Basically, I'm just focusing on design here, but if you're making a business and the business is surrounded about a product or an application or whatever, you can expand this to all the teams working on it. They need to kind of work closely together and understand the importance of each in their role. There are tools, and I just focus this one more on the mechanical, but the hardware or electrical team has tools as well that they're using to make simulations and do other things to predict what's going to happen before we actually make the thing and spend the money to make it and test it. And then the last one is basically, to show some of the challenges of developing products. That's why it's so important to know what's the use case, who's the end user, how is it going to be used, so that you can then set up at least some requirements around that, and you can design against that. I think somebody mentioned it earlier in the conversation we had earlier. You're never going to have all of them. Humans do crazy stuff to things. So, but you obviously want to limit that to just those crazy things and not as normal use case is a problem. And that is the end. So, questions?
I have something, it's not really a question, but while you were talking, it called to mind South Tech, which is a big industrial trade show. If you want to see some of these things in action in a trade show, Greenville, South Carolina, it's the week 24th, 25th, and 26th of October.
Okay. Yeah.
It's free.
Yeah.
So you can learn a lot.
They do have them in Charlotte too sometimes.
Right, the alternate.
Yeah.
I think First Tech is tomorrow, if I'm not mistaken.
Oh, really? Okay.
Yeah, that's first responders, technology.
Okay.
It's gonna be in Raleigh.
Okay. I didn't even know it was coming, honestly.
Can you repeat the name of the trade show?
South Tech.
South Tech.
TEC.
And the exhibit hall is absolutely free.
All right, we'll take another minute for any questions online. Apologies on the late lunch, but there is lunch out here, so everybody can go grab some pizza. And I'll keep this online for a few more minutes if we have any more questions.
How strong are the sintered metal parts relative to real material, solid material?
They're a little bit less strength because of the porosity, but I would say, depending on how porous you go, I mean, they're probably within 15% of it. So I did a product one time for equine, and it had two metal jaws, and that's how we made them, was for production. That's how they were made, and they were meant to release at 400 pounds. So they were pretty strong. They were only not big as your pinky. Any other questions? So the food is here.
Yeah,
Oh, thank God.
sorry.
So why don't we eat, and then I'm trying to stop sharing this thing, and then we will, for those who are interested, I'll be glad to show you around, show you some of the examples of products we're doing, and share our shop space and stuff.
So, you mentioned, how many as being an influence on tooling for mechanical.
Mhm.
Maybe you could talk a second about how many affects software and also electronics.
Well, honestly, on the software side, maybe I'd have somebody else talk about that. I'm not sure that let me first start with hardware, and then if you have a comment on software. So on the hardware side, the how many is more on the quantity of parts you have to get, and can you get the parts? A lot of times, what I see. Well, let me back up. On the design side of it, right? If you're making a lot of parts, let's say you were back in the cell phone day thing, right? You design your own custom chips, right? So high volume, it's worth it to put the engineering in to develop a custom chip or custom chip set to do this function that you want. If you're running middle or lower volumes, Texas Instruments is not going to do that for you. Okay, they're not going to make a custom chip for you. So that drives you then to using off-the-shelf stuff. And then depending on those off-the-shelf things, what some of them have an impact on size. Maybe what's off the shelf, what you could have done with a custom chip set in 1 or 2 parts, maybe it takes 10 parts to do it with, different individual components. So that drove now the size. Now the size of the product might have to be bigger than it did if we'd have developed a custom chip. And then last I'll say before I hand it over is then when it comes time to actually buy parts, the more volume you have to be careful on, can you get the supply of that part? What's the life of that part? If you're running a low volume type of a thing, even if you have a product, a component that's going end of life in 2 or 3 years, some of these components are pretty cheap. Maybe you just go ahead and buy your whole life thing. Instead of trying to redesign it for this end of life thing, you buy 20,000 of these chips and that lasts you 10 years. If you're in high volume, then you can't do that. If this is going end of life, you've got to do something to be able to account for that. So that's hardware mechanics. Any thoughts on software?
Yeah, from the software side, there's a couple different how manys to take into factor. How many people are going to be on a singular site? So, the amount of infrastructure you have to have for something like